Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. The focus of our AP Chemistry virtual lessons this week is on exam practice. I wanted to remind everyone that there is a new testing guide available. So if you do an internet search for 2020 AP Testing Guide, you should find the following document that was recently released by the College Board. And you can also go to cb.org/AP2020 to get this information. And it includes a variety of resources to help you get prepared for exam day. On exam day, you will need an e-ticket to test, so there's information about that. And again, that will either be accessible to you in your email, but you can also get it, students, by logging in to myap.collegeboard.org. There are 3 different ways that you can submit your responses to the online AP exam. You can either type it in a document and cut and paste. You can save a document and attach it, or you can handwrite your response, take a picture, and attach the photos. There is a AP 2020 exam demo, and that is live for you to log in, not really log in, but to actually practice and test to see if your technology is working. So you can go to cb.org/AP demo, and you can practice as many times as you want to try different methods of submitting your responses. So on exam day, there are a variety of things that you need besides your e-ticket. You'll need obviously your device and a particular browser. It says to recommend Chrome, Firefox, Safari, or Edge. Obviously a reliable internet connection or a cellular connection. And in terms of the specifics for AP Chemistry, you'll need the periodic table of the elements, and you'll need the equations and constant sheet. And there is also a keyboarding tip sheet if you choose to type and you're concerned about things like formulas or showing your work with respect to dimensional analysis. There is a tip sheet for typing responses. Again, you can go to cb.org/AP exam day docs to get this information. In terms of how do I take an open book, open note exam, you can go to cb.org/AP open book tips and get information about how to prepare. So I would strongly encourage you to have your study guides and resources available to you if you need to refer to that. So it's a good practice as you're watching these AP Chemistry virtual lessons to make a summary of the different units and the different important concepts and things like that. So on May 4th, you should receive an email confirmation that indicates your AP ID and a list of exams you're registered for. And then 2 days before each exam, you should receive an email with your personalized e-ticket. Again, you can also go to My AP and log in and see your e-ticket that way. If you go to cb.org/AP checklist, you can print out a checklist and kind of go through the things that you need for exam day. So on May 14th, that is the date of the AP Chemistry exam. So here I am on the East Coast. That would be at 2 o'clock in the afternoon. If you're located in the other end of the country in California, that would be 11 a.m. But again, there's a variety of times. You can figure out your time zone and where that would be. There are 2 free response questions on the AP exam this year. And you'll have 25 minutes and then 5 minutes to upload the first question, and then 15 minutes and 5 minutes to upload the second question. Again, you'll want to make sure that on exam day, you set up a good environment that limits distractions and make sure that you're all prepared with your technology. So what you'll do on exam day is you'll check in to your exam 30 minutes before the start time of your exam with your e-ticket. And then once the exam starts, it will start automatically, and then you can decide which format you're using. If there's multiple parts of the question, you can write A, B, C, D, and so forth. Then you will, again, pay attention to the time, make sure that you do submit your response on time. So again, we'll talk about this all next week as we continue to practice and prepare for the AP exam. And again, a variety of ways of submitting your response, either by attaching a file or by cutting and pasting. I had mentioned this earlier in another lesson about you can log in to myap.collegeboard.org and you can practice some questions. So you can click on AP Classroom and you can focus on practicing answering free response questions. And you can also look at the official scoring guidelines. So once you start a question and you type in your box there and then hit submit, you can click yes and then say yes review, and it would pop up a scoring guidelines, and you can make sure that you are matching your answer with the official scoring guidelines for various AP free response questions. And then once you submit that, then you can have your teacher take a look at it and get feedback from your teacher. All right, so today we're going to do 3 different FRQs. Hopefully you have access to scratch paper, something to write with, and a periodic table. Your first FRQ looks like this. It says, answer the following questions about iron, Fe, and aluminum, Al, compounds. So this is part A. Again, remember, I'm going to show you all the parts of the question. Then I strongly encourage you to stop the video and then solve this problem on your own, as opposed to just watching me go through and solve it. It'd be much more valuable for you to go ahead and solve this problem on your own before you have me tell you what the answers are. So again, this is part A. There is also a part B and a part C. They give you many different reactions here on this page. It says use the following reactions that involve iron and aluminum compounds to answer parts B and C. So here is part B. So it's got 2 subparts, and this is part C. And there are parts 1, 2, and 3 in that. So again, at this point, pause the video, go ahead and solve that problem. And then when you're ready, you can go ahead and press play and check your answers. So I'm going to make the assumption that you have done that. And I'm now going to start going over part A. All right, part A, Fe2O3 solid and Al2O3 solid have similar chemical properties. Some similarities are due to the oxides having similar lattice energies. Give 2 reasons why the lattice energies of the oxides are similar. Now, these 2 reasons have to do with essentially the law that you would normally invoke when comparing 2 different ionic compounds. So that's Coulomb's law. And of course, Coulomb's law works in a variety of settings. It has to do with the attraction between either charged particles or the attraction between polar molecules or the attraction between the nucleus and the electron. So just a variety of ways in which you can talk about Coulomb's law. So with respect to lattice energy, when comparing 2 different ionic compounds, you typically focus on the magnitude of the charges on the ions. That would be the Q1 and the Q2 in the numerator, as well as the size of the ions, which effectively represents the distance between these charged particles, and that's the R squared in the denominator. So for example, suppose we were comparing 2 different ionic compounds that had different lattice energies. What I might do if I was comparing sodium fluoride, NaF, which has a charge of +1 and -1, with magnesium oxide, MgO, which has charges of +2 and -2. And again, hopefully you have your periodic table handy and you can verify this for me. Then I would indicate that because of the greater magnitude of the charges on the ions, I would predict that magnesium oxide would have a greater lattice energy. If instead I was comparing 2 compounds, such as sodium fluoride and potassium chloride, in which the ions are both +1 and -1, then I might consider the periodic trend of atomic and ionic radii, knowing that since potassium and chlorine have larger radii than sodium and fluorine, I would say, okay, smaller distance between the charged particles, that would give sodium fluoride an advantage, in this case, having a greater lattice energy because the ions are closer together. Now, remember, in this particular question, we're not looking for differences, but similar. So similar lattice energies, and again, they said 2 reasons. Well, the 2 reasons are right here on the screen. And they are, let's talk about charge, and let's talk about the sizes of the ions. So these two reasons would be that both of these ions have the same charge, and that they must have similar sizes. You don't have to actually know the radii. That was not given to you in the problem, but if they have similar lattice energies, let's talk about charge, let's talk about the distance between the ions and therefore the ionic radii. So they are both same and similar. All right, on to part B. Now remember, we have all of these reactions here, and these reactions have to do with, we're going to be seeing these compounds over and over again. There's iron hydroxide along with aluminum hydroxide. So in part B of this question, Roman numeral 1, they give us a table with the KSP values for iron hydroxide and aluminum hydroxide. And they dissolved a 1 gram sample of each chemical separately, mixed together into 1 liter of distilled water. And they asked the following question: which ion, the iron or the aluminum, will be present in the higher concentration? And they were nice enough to say more than just justify your answer, but they actually went on to say justify your answer with respect to the KSP values provided. So if you are given a prompt that indicates you must justify your answer in terms of something specific to you that was given in the problem, then you should mention that. So as I compare the magnitude of the KSP values, I can recognize that the KSP for the aluminum hydroxide is larger. And that should mean something to me. So the KSP has to do with the dissociation of the solid ionic compound into the aqueous ions. So there are 2 separate KSP values, and this one is larger. So therefore, if it's a larger KSP, I would expect that the concentration of the aluminum ion would be present in a higher value because of the larger value of the KSP. Now, what's also nice about this comparison is that we have the same stoichiometry. We're not comparing, for example, a 1-to-3 ratio with a 1-to-1 ratio. Because they have the same 1-to-3 ratio between moles of the cation, the metal, and moles of hydroxide, then I can go ahead and make this a nice clean comparison and say that whoever has a greater KSP value should have a higher solubility. So the answer is that the aluminum 3+ ion will be present in the higher concentration. Both compounds have the same stoichiometry, the same mole ratio, and aluminum hydroxide has the greater KSP value. Okay, on to part II of this question, part B. Write a balanced chemical equation for the dissolution reaction that results in the production of the ion. So they can't go ahead and tell you whether it was aluminum or iron because it says that whatever you chose in part 1. So because we chose aluminum, then this would be our equation. In fact, there was another acceptable answer to this question. If we go back and take a look at all of those reactions, those 9 reactions, it is possible that you could still get the production of aluminum hydroxide as aluminum oxide reacts with water to form aluminum hydroxide. So then if you were to go on, 2 aluminums would be present and a total of 6 hydroxides would be present. So what you could do is you could start with these reactants right here, and then you could finish with these products, and that would still be correct. So on the official scoring guidelines, this was also a possible correct answer. All right, we're going to move on to part C of this question. Students are asked to develop a plan. This is a great question for considering that we have laboratory procedures. And again, in terms of error analysis and experimental design, this is a good thing for us to focus on right now. A plan for separating the aluminum oxide from a mixture that contains both iron oxide and aluminum oxide. Now, one student proposes that the aluminum oxide can be separated from the mixture by simply adding water and filtering. Now, that would mean that we have our mixture. So we've added the water to it, and then you'd have to pour that through some kind of a funnel and separate the solid. Well, the problem with that technique, it says, explain why this is not reasonable. Even though there is a slight difference between the KSP values for iron and aluminum hydroxide, it's a very small difference. And so if you're going to separate one compound from another, there needs to be a pretty significant difference in the KSP value. So the approach of separating one from the other based on solubility, that only works if there is a significant difference in water solubility between the two substances. And unfortunately, 10 to the negative 33 and 10 to the negative 38 as the magnitude of these KSP values, they're both very, very small. There's not a significant difference in the water solubility of those two compounds. All right, so in the next part, so part II of part C, a second student organizes a plan using a table. And they've already filled in the first two steps. So step 1, add sodium hydroxide, NaOH, to convert the aluminum oxide to the aluminum hydroxide, and then to this sodium aluminum compound. Now, that came from reactions 2 and 4. So in reaction 2, they add water to produce aluminum hydroxide, and then reaction 4, only one of the chemicals was converted into something that is aqueous and therefore soluble. So that means that it can be filtered. And that's what they're doing in the next step. They are filtering out the solid that did not dissolve from the mixture that did and save the filtrate. So if you're wondering what exactly is the filtrate, so I'll just go ahead and draw my funnel again. So because the iron hydroxide is insoluble, that's going to be collected on the filter paper. But then what comes through in terms of solution, that is the filtrate. And the filtrate would contain this soluble sodium aluminum compound. So they're separating the insoluble iron hydroxide from the soluble sodium aluminum aqueous compound. Now it goes on to say, complete the plan by listing the additional steps that are needed to recover the aluminum oxide. So our job is to get aluminum oxide out of that filtrate. So our goal is to get aluminum oxide produced. So this would be a nice reaction to use, reaction 9, but that assumes that we have solid aluminum hydroxide. So we could create some solid aluminum hydroxide by reacting this material that's in the filtrate with hydrochloric acid. So in my opinion, based on the things we have here, and we're trying to get to solid aluminum oxide, I think our next step, step 3 in this process, is to react the material, the filtrate, from that filtrate, which is soluble, we want to convert it into an insoluble aluminum hydroxide. Then we can go ahead and we can filter this, and then we can heat it according to reaction 9. So that's our plan. Let's react it with some hydrochloric acid to produce insoluble aluminum hydroxide. Let's go ahead and filter the aluminum hydroxide from the rest of the solution, and then we can heat that solid aluminum hydroxide to turn it into aluminum oxide. So step 3, let's add HCl to the filtrate until a precipitate of aluminum hydroxide is formed. That was reaction 7. Then we can go ahead and filter out the solid aluminum hydroxide, and then finally we can heat the solid aluminum hydroxide to form aluminum oxide. All right, now we're not quite done with part C. There was a third part, part III, and it goes on to say that we have 5.5 grams of aluminum oxide that was recovered from a 10-gram sample of the mixture. So we have a mixture that contains 10 grams. And they would like us to calculate the percentage of aluminum by mass in this mixture. So our job is to figure out how many grams of aluminum are there in this mixture. Then we can multiply by 100 and convert that into a percent. So we're going to have to find a way to convert 5.5 grams of aluminum oxide. This might involve several steps into grams of aluminum. Now, once we can do that, we can then go ahead and figure out what that number is for the grams of aluminum. Hopefully you can see that this is going to be a little bit of stoichiometry. Okay, so it's the periodic table to go from grams to moles. And the periodic table tells us that since aluminum weighs approximately 27, so we have 2 of them, that's around 54. Oxygen weighs 16 on the periodic table. We have 3 of those. So that would be 54 plus 48. That's, again, about 102. So I did the math using the atomic masses on the periodic table, and that's my molar mass of aluminum oxide. Now, of course, there are 2 aluminums in the formula. So there are 2 moles of aluminum for every 1 mole of Al2O3. Then we have to go back to grams using the periodic table and the molar mass of aluminum. If we do this math, 5.5 divided by 101.96 times 2 times 26.98, we get our grams of aluminum. I'm going to round this off to 2 sig figs, and I get 2.9 grams of aluminum, and that was present in a 10-gram sample. So when I do times 100, I get 2.9 divided by 10 times 100. That's about 29% aluminum by mass. All right, so we have now reached the end of the first free response question. I hope that was helpful in terms of checking your answers. I'm now going to show you the screens for the next free response question. So this is parts A, B, and C. It says elemental sulfur can exist as molecules with the formula S8. They're showing us an incomplete Lewis diagram connecting 8 sulfurs. That's parts A, B, and C. This is part D. You can see a photoelectron spectrum, and they have some questions about that. And there is also a part E of this question, and that is right here. This is about kinetics and reaction rates. And then finally, there is a part F. So again, at this point, I strongly encourage you to stop the video, solve all of the parts of this question, and then once you've gotten answers to parts A, B, C, D, E, and F, then you can go ahead and press play. So I'll make the assumption that you have already done that, and therefore you're going to go ahead and check your answers to this question. And I'm going to start with part A. All right, we are given this Lewis structure, which is not complete. And then it goes on to say in part A that the diagram shows only bonding pairs of electrons. Okay, so what we are looking at is the dash connecting the atoms. Okay, this is a bonding pair of electrons. Now there's also non-bonding or lone pairs of electrons. How many lone pairs of electrons does each sulfur atom in the molecule have? Now to review valence electrons with you, I just picked period 3, which is from sodium all the way to argon, and we should know that the valence electrons are going to be from 1 to 8. So focusing on sulfur, sulfur has a total of 6 valence electrons. If I were to draw the Lewis dot structure for just a sulfur atom, I would have to draw 6 dots. 1, 2, 3, 4, 5, 6. If I wanted to make a simple molecule, for example, dihydrogen monosulfide or H2S, I might bring in a hydrogen and then another hydrogen, which each has 1 valence electron. And so you can see I've got some bonding pairs of electrons in these dashes, but then I would also have non-bonding or lone pairs of electrons that are located here and here. So that's going to be the structure. That's what we see for this molecule. So each sulfur atom contains 2 lone pairs of electrons. All right, let's move on to part B. Based on your answer to part A, determine the expected value of the SSS bond angles in this molecule. I'd like to remind you about molecular geometry. So remember we learned about Vsepr theory. That was back in Unit 2. We talked about valence shell electron pair repulsion theory, and we looked at different types of hybridization of the central atom. So for example, if I have 4 electron domains, that's sp3, the bond angle is typically 109.5. If I have only 3 electron domains, It's sp2 hybridized for the central atom, and that's a bond angle of 120 degrees. And of course, if I have sp, which would be linear, that's 180 degrees. So our sulfur atom, according to the answer in part A, has 2 bonding pairs of electrons coming off of it, and then it also has 2 non-bonding pairs of electrons. So this is looking like 109.5. Each sulfur atom should be sp3 hybridized. So I'm going to say 109.5 for part B. The acceptable range of values for this question was anywhere between 104 and 110. And a little interesting note, the experimentally determined bond angle for this molecule works out to be 107.8. So as long as you were in that range between 104 and 110, you were good. So I just said 109.5. All right, moving on to part C. Write the electron configuration for the sulfur atom in its ground state. Let me remind you about electron configurations. We have hydrogen and helium, and that's 1s. So if I was just going to write the electron configuration for helium, it'd be 1s2. Then we get to the second row of the periodic table. So lithium and beryllium, that would be 2s. If I was going to write the electron configuration for beryllium, I would say 1s2, 2s2. If I had to go on to boron, it would be 2p. So 2p1 for boron, and then 2p2 for carbon, and then 2p3, 2p4, all the way up to neon would be 2p6. If I go around the corner, now I'm at sodium and magnesium, that would be 3s. So either 3s1 or 3s2 for magnesium. And then on to trying to get to sulfur. So I'm not going to go all the way. If I was going all the way to argon, I would have said 3p6. I'm stopping right here at sulfur. So 3p1, 3p2, 3p3, and then I would say 3p4 for sulfur. And just to remind you that after 3p, you would have 4s, and then 3d for the transition metals in the middle there, and then 4p, and then that pattern continues, 5s, 4d, 5p. So again, hopefully that's the way you think about electron configurations. So I've got my electron configuration for sulfur, and it's going to be either the full configuration, or I could put neon in brackets to abbreviate these 10 electrons and write neon, and then 3s2, 3p4. All right, moving on to part D of this question. The complete photoelectron spectrum for the element chlorine is represented below. So chlorine is right next door to sulfur on the periodic table. Sulfur is atomic number 16. Chlorine is atomic number 17. So we should have 17 electrons total, and with a PES, photoelectron spectrum, you can literally read the electron configuration right off the chart from left to right. Notice that the x-axis has higher values on the left. That's because the 1s orbital contains the electrons that are closest to the nucleus and most difficult to remove. So they have the highest binding energy because they have the strongest attraction to the nucleus. And as you continue going further and further out, so 2s, 2p, notice that the peak for 2p is 3 times higher than the peak for 2s. So the height of the peak, the relative number of electrons, tells us how many electrons are in that particular subshell. So 2s2 and 2p6 makes sense that we have the peak for 2p being 3 times larger. 3s, but I'm not going to go all the way to 3p6. Notice that the peak on the very end there, peak y, stops just shy of the 6. It stops at 5, but that's consistent with the electron configuration for chlorine. So chlorine's electron configuration, 1s2, 2s2, 2p6, 3s2, and then 3p5. All right, it goes on to say that the electrons in peak x, which corresponds to the binding energy of a certain orbital, it's 273 megajoules per mole. So that's how much energy is required to remove those electrons. Now for sulfur, for the same orbital, it's going to be a smaller number, so 239. So for this Roman numeral 1, identify the orbital, so we know it's going to be 1s, and then explain the difference between the binding energies in terms of Coulombic forces. Now, we talked about Coulomb's law earlier. We'll talk about it again. So the binding energy for the 1s orbital is 239 megajoules per mole for sulfur, and it is higher. It's 273 megajoules per mole for chlorine. Now, we're not going to talk about the distance between the nucleus and the outer shell. There is not a significant difference in size. Typically, when you're comparing size, you typically have to go down the group. So for example, if I was comparing, let's say, oxygen with sulfur, with selenium, there is a rather significant difference in size as we go down. Here we're talking about two elements that are in the same period. So the most significant difference here has to do with the charge. Chlorine, which has 17 protons, having one more proton than sulfur, the 1s electrons in chlorine experience a stronger attraction toward the nucleus than the 1s electrons in sulfur. So when you think about why does size get smaller as you go from left to right across a period, it's because of increasing nuclear charge. So again, you could say nuclear charge or simply more protons. So the peak X is the 1s orbital. And because chlorine has one more proton than sulfur, the 1s electrons in chlorine experience a stronger attraction. Okay, so we have explained the difference. And now we're on to part II of this question. They're talking about peak Y. So again, we talked about how this is 1s, 2s, 2p, 3s, and then right here would be 3p. So peak Y corresponds to the electrons in certain orbitals of chlorine atoms. On the spectrum shown, carefully draw the peak that would correspond to the electrons in the same orbitals of sulfur atoms. So there are two significant differences between the 3p orbital of sulfur and the 3p orbital of chlorine. The first one's kind of obvious, and that is that the height of the peak is going to be different. We're talking about 4 electrons in the 3p orbital as opposed to 5 electrons. So if I were to draw the peak, I would have to stop at this level. But the other difference, we just talked about the difference in the number of protons. So if chlorine has more protons, that is a higher binding energy. We can say that the other way. If sulfur has fewer protons, that would mean that the binding energy for the 3p orbital for sulfur should be a little bit less than the binding energy for the 3p orbital for chlorine. So not only should I draw this smaller in terms of the peak height, I think if I were drawing this, I would have to sketch this peak a little bit further to the right, indicating a slightly smaller binding energy. And that's what the official scoring guidelines show you. So this peak is further to the right because of the smaller binding energy, because sulfur has one fewer proton. So therefore it has a slightly smaller attraction. And those electrons are slightly easier to remove. And of course, the peak height being only 4 electrons in the 3p orbital for sulfur. All right, so we go on to the next part of this question. This is part E. And now we're talking about the reaction between sulfur and hydroxide. This is a kinetics experiment. So we have a student who is studying the kinetics of the reaction represented above and obtains the data in the following table. So part I of part E says, determine the order of the reaction with respect to S8. Justify your answer. So before we analyze trials 1 and 2, just want to remind you about rate laws. So you could have a 0 order rate law. So that means the concentration of the reactant A raised to the 0 power is just 1. You could have a first order rate law. So the rate constant times the concentration of A to the first power. And you can have a second order rate law. So the rate equals the rate constant times the concentration of A to the second power. What would happen if you, to the initial rate, if you tripled the concentration of A? Well, for 0 order, it would make no difference because there's no concentration of A term featured. Then the initial rate would remain constant. That's what 0 order would look like. If instead you tripled the concentration of A, well, then for a first order rate law, then you would triple the rate. But since 3 times 3 is 9, then 3 squared, that represents if you were to triple the concentration of A and it was second order, the initial rate would increase by a factor of 9. Now let's go look at our table and see what happened between trial 1 and trial 2. So in going from trial 1 to trial 2, they tripled the concentration of the sulfur and they kept the concentration of the hydroxide constant. So we can focus only on the effect of the concentration of sulfur on the initial rate. Comparing 0.699, that's practically 0.7, to 2.1, since 7 times 3 is 21, hopefully you can see that we tripled the initial rate, indicating that this is a first order reaction. So to determine the order, this is first order. I'm going to show you the official scoring guidelines. You have 2 choices here. You could explain it in words, or you could explain it mathematically. Either way, it's going to be first order. The reaction is first order with respect to the sulfur because when comparing trials 1 and 2, tripling the concentration of sulfur while keeping the concentration of hydroxide constant results in tripling of the initial reaction rate. Or mathematically, you can put rate of the second trial divided by rate of the first trial, so you get 3. And then when you plug in these numbers, this part will just divide out because the concentration of hydroxide didn't change. And now we have essentially 3 raised to the x power, where x is the order, x is 1. All right, the next part, we have the question mark in the table. Determine the value of the hydroxide concentration that was used in trial 3, and they're coming out and telling us that the order is also first order with respect to the other reactant. So we have first order with respect to sulfur, and we have first order with respect to hydroxide. So there is our overall rate law. One way you can solve for this question mark is you can go ahead and calculate the value of K. So in trial 1, we have a initial rate of 0.699 molarity per second, and that equals the rate constant, which we don't know yet, times the initial concentration of sulfur, which is 0.1 molar, and then times the initial concentration of hydroxide, which is 0.01 molar. Again, we know that they're first order because we figured it out in part Roman numeral 1 of this, and then they told us it was first order for the hydroxide. Let me go ahead and do the math and solve for K. So 0.699 divided by 0.1 divided by 0.01. So the value of K is 699 inverse molarity inverse seconds. I'm now going to go to trial 3. I know the rate is 4.19 molarity per second. I was just able to calculate the value of K, so I plug that in. The initial concentration of sulfur is 0.3, and I'm solving for the concentration of hydroxide. Now, when I do this math, 4.19 divided by 699 divided by 0.3, I get 0.02. I wonder if there was an easier way to solve this. What I just did wasn't a bad way. It was a fine way to solve it, but take a look at this comparison between trial 2 and 3. These concentrations did not change. The rate was doubled. We already know it was first order with respect to hydroxide because they told us that. So you could have just done the following. Without even solving for the rate constant, you could have just said, comparing trials 2 and 3, sulfur is kept constant, the initial reaction rate doubles, and since we know it is first order with respect to hydroxide, then the concentration must be twice as much. So again, they got the answer, which was 0.02 moles per liter. So either solving for K or simply comparing trials 2 and 3 with all the information that was known and given, that could have given you the answer. All right. Part F. The next day, the student does trial 4 using the same concentrations of sulfur and hydroxide as trial 1, but the reaction occurs at a much slower rate than the reaction in trial 1. The student observes that the temperature in the lab is lower than it was the day before. Using particle level reasoning, provide 2 explanations to help account for the fact that the reaction rate is slower. Now we've got to talk about particle level reasoning. So do not say that the reaction rate is slower because the temperature is lower. That's not a particle level explanation. So what I have here are just some particles that are just moving around inside a container. And now what we're going to do is we're going to decrease the temperature. So what's going to happen to those particles? Hopefully, you know that when you lower the temperature, and temperature has to do with kinetic energy, you also decrease the speed of the molecules. And since reactions occur because of collisions, then the number of collisions, or you might say the frequency of the collisions, is going to decrease. And if the frequency of the collisions decrease, that would lead to a lower reaction rate. But they said two explanations. So decreasing the frequency of the collisions, that's only one explanation. So what's the other one? Well, if I go back to, let's say, Unit 3, talking about intermolecular forces, you have seen diagrams like this before in earlier virtual lessons. So when you raise the temperature, you increase the average kinetic energy. When you decrease the temperature, you decrease the kinetic energy. And with respect to vapor pressure, you can lower the vapor pressure because now there's a smaller fraction of molecules that have enough energy to escape the liquid. We have also seen, with respect to reaction rates, that when you change that to activation energy at a lower temperature, there's going to be a smaller fraction of the molecules that have the requisite energy needed to get from reactants to products. So in your official answer, you should not only talk about the frequency of collisions, but also the energy of the collisions. So there were fewer collisions that had sufficient energy to react, and there simply were a lower frequency of collisions because the average speed of the particles is lower. So talk about energy and talk about frequency. All right, now considering that we're getting close to the end of our time together, I'm going to have to do a little rush, as well as appreciate the fact that this is good FRQ practice. This particular lesson might run a little bit longer than normal. So hopefully you'll forgive me for that and indulge the fact that we are taking some good opportunities here to do FRQ practice. So your third FRQ has parts A. This is part A. Part B. And then there is also parts C and D. So as I mentioned before, this is when you should pause the video, solve this problem on your own, and then press play to go ahead and check your answers. So I will probably rush a little bit through the explanations. I apologize for that. I'll do my best to explain things clearly, but I do want to pay attention to time here. Okay, so I'm going to assume that you have already answered parts A, B, and C and D. All right, let's take a look at the answers. Answer the following questions relating to HCl, CH3Cl, and CH3Br. So HCl can be prepared by the following reaction, and a student claims that the reaction is a redox reaction. Is the student correct? Justify your answer. Well, if they are correct, you had better show a change in oxidation numbers. So there should be oxidation numbers either increasing or decreasing as you go from the reactants to the products. If you disagree with the student's claim, then you should also justify your answer in terms of the fact that the oxidation numbers are not changing. I'm going to start with H2SO4. Hydrogen is normally +1, and we have 2 of them. So that's +2. Oxygen in most compounds is -2, and we have 4 of them. So we have a total of -8. So that makes the sulfur, to make this total 0, total charge 0, we have to have the sulfur of oxidation number +6. If I then go to the other side of the equation, which is Na2SO4, I can recognize that the SO4 is going to be identical. It's the sulfate ion. Sodium is still +1. So nothing has changed for sulfur or oxygen. Sodium chloride is a very typical alkali metal, halogen type compound. So +1 -1 is not unusual. And then H and Cl, we're going to go ahead and let hydrogen be the normal +1 oxidation state when bonded to nonmetals. So as you can see, the oxidation numbers of hydrogen, sulfur, oxygen, sodium, and chlorine are not changing. So is the student correct? No, the student is not correct. None of the oxidation numbers of the elements change. So you have to validate the claim, or I should say disagree with the claim, and then validate your reasoning with talking about oxidation numbers. All right, the next part of this question says to calculate the mass of sodium chloride needed to react with excess H2SO4 aqueous, so that's a solution of sulfuric acid, to produce 3.00 grams of HCl gas. This is just a straight up grams to grams conversion. And that typically is done to go from grams of one chemical to grams of another. You're going to use what I would call the periodic table, followed by the coefficients, and then followed by the periodic table. So what I mean by that is you're going to have to use the molar mass. So we know that 1 mole of HCl has a certain mass. The periodic table can help you there. Then we're going to go from moles of HCl to moles of the other chemical, which in this case happens to be sodium chloride, and they already gave us a balanced chemical equation, so we know what those coefficients are. Then you have to go back to the periodic table because we have to get to grams. And again, the periodic table can help you convert from moles to grams. So if you do that, that's how much HCl weighs. That would be hydrogen plus chlorine. So the atomic masses add together to give you 36.458. There's our 2-to-2 ratio from the balanced equation. And then sodium plus chlorine, the atomic masses add up to give you 58.44. So if you start with 3 divided by 36.458 times 2 divided by 2, that's obviously a ratio of 1, and then times 58.44. I'm going to round that off to 3 significant figures. 4.81 grams of sodium chloride is your answer. Okay, let's move on to part B. We have a different chemical reaction. HCl can react with methanol vapor, CH3OH, to produce CH3Cl. And they give you a balanced equation with a value of K, 4.7 times 10 to the 3 at 400 Kelvin. We have a sealed reaction vessel, volume of 10 liters. We have the pressure of the CH3OH, and we have the pressure of the HCl. So in this sealed vessel, we have 0.250 atmospheres for the methanol vapor. And then we have 0.600 atmospheres for the HCl gas. And again, this is all inside our reaction vessel. Does the total pressure increase, decrease, or remain the same as equilibrium is approached? Now, the pressure could increase if we have more moles of gas. The pressure could decrease if we have fewer moles of gas. So let's take a look at our equation. Well, I see 2 moles of gaseous reactants, and I see 2 moles of gaseous products. So in fact, the total pressure in the vessel should remain the same. So the pressure will remain the same because the reaction stoichiometry shows that 2 moles of gaseous reactants produce 2 moles of gaseous products. So because the total number of moles of gas does not change, the pressure does not change. All right, on to the next part. Considering the value of Kp, which is about 4,700 here, calculate the final partial pressure of HCl after the system inside the vessel reaches equilibrium. Now, I'd like there to be a little deja vu. If you guys have been watching these videos, we've talked about other examples like this. So this one was one I talked about before. It also had a rather large value for the equilibrium constant. And what I had said in referring to topic 7.5 from the AP chemistry curriculum is that some equilibrium reactions have very large values of K, others have very small values of K. But the ones that have large values of K essentially proceed to completion, whereas the very small values of K are essentially reactants and barely proceed at all. So the official scoring guidelines here treat this like a limiting reactant problem. It says the value of Kp is large, so the reaction will proceed to the right until the limiting reactant is used up. So we had 0.6 atmospheres for the HCl, and we had 0.25 atmospheres for the CH3OH. And as you can see in this little rice table, the CH3OH would go down by essentially 0.25. And then that same amount, because of the 1-to-1 mole ratio, you can treat mole ratios and pressure ratios the same. So we're doing this rice table in terms of pressures because they are proportional to moles. And now we get effectively not much CH3OH left, and 0.6 minus 0.25 is 0.35. So the pressure of HCl at equilibrium is 0.35 because we can treat this like a limiting reactant problem. Now, I said it's essentially 0 for the methanol, but it's not actually 0. It's just a really, really small number. So the student claims that the final partial pressure of the CH3OH in equilibrium is very small, but not exactly 0. So yes, I would agree with that claim. So the value of this CH3OH would be extremely small, but there should still be some molecules present because it is equilibrium. And a dynamic equilibrium is that we have both a forward and a reverse reaction occurring at the same rate. So they went ahead and plugged in the numbers 0.25, 0.25, and 0.35 for the pressures of all the chemicals except for this. And when they set the equal to the K and solved for it, they got the value, which is really small. You didn't have to do that, but somehow indicate that the value of the pressure of CH3OH is very, very small, but not 0, because there should still be some of this reverse reaction occurring at equilibrium. All right, so the last part has to do with IMFs and then something about pressure. So again, hang in there. We're talking about CH3, Cl versus CH3, Br. These molecules are not symmetrical. The dipoles do not cancel out, so they are both polar. But interestingly enough, the CH3Br has a higher boiling point. And the reason I say interesting is because it's not just based on polarity, because the dipole moment for CH3Br is actually not greater than the dipole moment of CH3Cl. So if these are two polar molecules, we can't really say that one of them is more polar than the other, and that's why the CH3Br has a higher boiling point. So it must have to do with something involving London dispersion forces. So when you go from chlorine to bromine, larger electron cloud leads to stronger polarizability and London dispersion forces. All right, so identify all types of IMFs. Because these are polar molecules, they experience both LDFs and dipole-dipole forces. And why is the boiling point of CH3Br greater than that of CH3Cl? It's because the electron cloud in CH3Br is larger and more polarizable than that of CH3Cl. So the London dispersion forces are stronger in the bromine compound than they are in the chlorine compound. So you couldn't talk about polarity there. And again, you've got the numbers right in front of you. It's not about one molecule being more polar than the other. It's about the size of the electron cloud. All right, so what they did was they took a sealed vial that contained this chemical, CH3Cl, in liquid form, and they had it stored in a freezer, and then they want us to calculate the pressure in the vial if it was removed. And now it's at room temperature, 298. So here's my ideal gas law. PV equals nRT. We have pressure we're solving for. I don't know the number of moles yet, but I use the ideal gas constant from the AP equation sheet. We're talking about the pressure at 298 Kelvin. And the volume, I'm going to deal with that in just a moment. That's the volume of this inside this vial. So to get my moles, I'm going to have to just convert 1 gram of CH3Cl into moles. That's a quick little periodic table, molar mass. And that number, 0.0198, goes into my expression for the ideal gas law. Of course, 2 milliliters is not the same as 2 liters. If you divide by 1,000, 2 divided by 1,000 is 0.002. And we do this math. Let's see what the pressure is inside the sealed glass vial. Now you have to check your calculator. In fact, if you check it, it is correct. Wow. The pressure inside that vial would be 242 atmospheres. Well, that kind of takes care of the next part of this question. Explain why it would be unsafe to remove the vial from the freezer and leave it on a lab bench. It would most likely explode because of the extreme pressure there. So at room temperature, the liquid will vaporize, and consequently the glass vial is not going to be strong enough to withstand that increase in pressure. Okay, done. We went through today in this lesson 3 different FRQs. Thank you for hanging in there. Again, there are helpful chemistry resources in the video description. And once again, if you go to cb.org/AP 2020, you can get more information about the AP exam. This has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Thanks for watching.